We're going to start today by examining problem number 1 from midterm exam number 1, which involves the pelican diving into the ocean. In a recent lab, you studied the motion of an object falling under the forces of gravity and air resistance. Your friend has asked you to help her with a similar experiment that involves testing a model for the motion of a pelican as it dives below the surface of the ocean. From direct observation, she knows that pelicans enter the water with a speed of 15 meters per second at an angle of 20 degrees from the vertical line drawn perpendicular to the surface of the water as indicated in the diagram. Current pelican theory predicts that as they dive through the water, they experience a drag force proportional to their speed cubed, v cubed. The code listed on the next page, which is nearly identical to your computer model from lab, is missing a few lines of code. In the spaces provided, add the statements necessary to predict the motion of the pelican. The objectives of this problem are as follows. You first have to determine the initial velocity vector of the pelican. You have to determine the net force acting on the pelican, determine the final position and the final velocity of the pelican as it dives through the ocean's waters, and then also complete the skeleton V Python code with the appropriate lines according to Newton's second law. The first thing that one must do is find the x and y components of the pelican's velocity. Because the problem states that the initial velocity is equal to 15 meters per second, one can use trigonometric functions to determine both the x component of velocity and the y component of velocity. So if you take the cosine of the angle multiplied by the initial velocity, one can find the y component of the pelican's velocity. And if you do the same but use sine, one can find the x component of the pelican's velocity. Note that the y component has a negative sign in front because it's traveling downwards. Before stepping forward with the problem, one must consider other parameters which are given by the problem. We know that the mass of the pelican is equal to 15 kilograms. The pelican initially starts at the origin at 0, 0, 0, shown in vector format. Time is equal to 0. The delta t time step is relatively small compared to t, which is 0.001. G, as it always is, the gravitational attraction of Earth, is 9.81 meters per second squared. And in this case, b is the drag constant acting on the pelican, is equal to 1.2. Because the pelican is interacting with the Earth, there must be some gravitational attraction between the pelican and the Earth. This results in a weight force, which is the product of the mass of the pelican multiplied by the gravitational acceleration on Earth. So shown here, Fw is equal to m times g, and we know that m is equal to pelican.m, which is 15, and g is equal to 9.81, always the same on Earth. Shown below is how it will be modeled in the V Python code, pelican.m times negative g, because this is acting in the downward direction. Now the pelican also experiences a drag force when traveling through the water with an initial velocity. As a result, Fd, the drag force, is equal to the drag constant b multiplied by the pelican's velocity, and again multiplied by the squared magnitude of the velocity. The velocity is multiplied together 3 times because the drag force is proportional to the speed of the pelican cubed, v3. So shown here, the drag force is equal to b times the magnitude of v squared, and in v Python format, negative b, acting opposite of the direction of motion, times pelican.vel times magnitude squared of pelican.vel. In order to find the total net force, you have to add both the forces acting on the pelican together. So here, Fnet is equal to Fw, the weight force, plus Fd, the drag force, acting on the pelican. The next step includes finding the new velocity and the new position of the pelican through a while loop in VPython. But through Newton's second law, we know that Vf is equal to Vi plus Fnet divided by m times delta t. This is Newton's second law. Therefore, we can apply Newton's second law to find the new velocity using the Fnet which we calculated in the step prior to this. And also, we know that a change in position is defined by the change in velocity multiplied by a change in time. In order to find this final position which we are looking for, we can manipulate this formula accordingly to find Rf, the final position. Now in Python, the velocity must be in vector format, so when you consider the x component, the y component, and the z component, it turns out to equal pelican.vel is equal to vector, parentheses, of the x component, 15 times the sine of the angle 20, and the y component, negative 15 times the cosine of 20, the angle which the pelican dives in at, And remember, this is negative because it travels downward in the y direction, and it travels 0 at a speed of 0 in the z direction. From this velocity vector, we can now find the net force and the new velocity and position of the Pelican as it dives through the water. So we set the weight force equal to the vector of 0, negative g times Pelican.m, which is the weight force, and 0. And then drag force is equal to negative b, which remember is opposite of the direction of motion, times the Pelican's velocity, times the magnitude squared of the Pelican's velocity. And when you add these two forces together, you find F net. Using F net, we can find the velocity via Newton's second law, and then from there, find the position of the Pelican through the change in velocity multiplied by the change in time. This completes the Exam Wrapper 1 video for Problem 1 from Midterm number 1. Thank you.